Hello there. Today we're going to have a look at the first part of the Waves unit at Higher Physics, Waves and Interference. Before we start that though, we need to remember a little bit of the fundamental properties of waves from National 5 Physics. So this purple wave represents a transverse wave, and a few things about it. Between the crests of the wave, or indeed between the troughs of the wave, is equal to 1 wavelength. The amplitude is the size of the disturbance of the wave, so from the midpoint up to the crest or from the midpoint down to the trough. And a few formulae as well. F equals n divided by t, which stands for frequency equals number of waves over time, measured in hertz, which is the key definition of the frequency of a wave, number of waves per unit of time. F equals 1 divided by capital T, which means frequency equals 1 divided by period. So frequency is 1 over the time for one complete cycle of the wave. V equals F lambda, which stands for speed equals frequency times wavelength. And V equals D over T, speed equals distance over time. Now, on to the new stuff. Waves can interfere with one another. And they can interfere in a couple of different ways. Firstly, if two waves are in phase. Now, what I mean by being in phase, I mean that the crests of two waves are lining up with each other and the troughs of the two waves are lining up with each other. So in this case, these two waves are in phase. And if they meet in phase, then the crests will meet crests and create taller crests. And the troughs will meet troughs and they'll meet deeper troughs. And that gives rise to something called constructive interference. So we get the crests adding up to give taller crests and the troughs adding up to give deeper troughs. I think a little bit like digging holes in your garden. If you have a hole in your garden, then you have a hole and a pile of earth. If you dig a deeper hole in the bottom of that hole, then you get a deeper hole and you end up with a bigger pile of earth as well. So that is constructive interference. The other way that waves can interfere is if we have the waves meeting out of phase. So the crest of one wave meeting the trough of the other wave and vice versa. Now when that happens, we get what's called destructive interference. So the wave effectively cancels itself out. A little bit like, again, the analogy of having holes in the ground in our garden. If we have a hole in the ground, then we've got a big pile of earth next to it. But if we put a pile of earth into the hole in the ground, then we no longer have a pile of earth and we no longer have a hole in the ground either. So they cancel each other out. Now, if we've got what we call coherent waves, then coherent waves are waves which have the same frequency in the wavelength and a constant phase relationship. That means if they're in phase, they're always in phase at that point. If they're out of phase, they're always out of phase at that point. Now, this can be achieved by having two loudspeakers, for example, producing the same sound wave at the same time, like that diagram there. Or it can be created by taking an original wave and then splitting it. So if you take a light wave and shine it through two slits, then we get the light wave split into two parts, two identical coherent waves. Now, if we have coherent sources interfering with each other, we get what's called an interference pattern. And this little animation here shows us an interference pattern of some waves. So the red lines represent the crests of a wave. And you can see they are coming along from the left, colliding with a barrier and splitting into two parts. When they meet, we can see there are three bits where, if we look along the middle, we've got the waves overlapping with each other, but that also happens here and here. And in between those lines, we've got places where the waves are exactly not overlapping with each other. all the way along those lines. Now, what's going on here? Well, here's a similar thing. The solid lines in this diagram, the solid blue lines, represent the crests of a wave, and the dashed lines represent the troughs of waves. Now, if we pick some points on that diagram there, this point here, for example. Now, that point there is exactly the same distance from both of the sources. So it's 4 waves from source 1 and 4 waves from source 2. So the 2 waves have travelled exactly the same distance to get there. It's 2 crests meeting each other, and therefore we get constructive interference. The fourth crest from source 1 and the fourth crest from source 2 meeting, giving constructive interference. So we get what's called a maxima at constructive interference. And here, because the 2 waves have travelled exactly the same distance, we say the path difference to that point is 0. Now, let's consider another point, this one here. Now that point there is 3 whole waves from source 1, but 3.5 waves from source 2. So now it's the third crest from source 1 meeting the third trough from source 2. So we've got a crest meeting a trough, which is giving rise to destructive interference. And because one wave has travelled half a wave further than the other, we say at that point the path difference is half a wavelength. So all the way along that orange line that red X lies on is the path difference is half a wavelength, and we get destructive interference. And the same happens on the opposite side as well, where we'd be half a wave further from source 1 than from source 2. Let's investigate one more point. So here at the green X, now that green X happens to be 4 whole wavelengths from source 1, but 5 whole wavelengths from source 2. So now we've got the 4th crest from source 1 meeting the 5th crest from source 2. So although it's not the same crest and trough meeting each other, we're getting constructive interference again because it is a crest meeting a crest. So here, one wave has travelled a whole wave further than the other, so the path difference is 1 wave. And we get a maximum again. If we work our way outwards a little bit further, we get to the point where the waves have travelled 1.5 waves further in either direction, and we get a minima again, because a peak is meeting a trough. And then if we go even further still, we get the point where one wave is travelling 2 whole waves further than the other, and we get a maxima again. And that brings us to a slightly different animation. So here, point P is midway between source 1 and source 2. Let's look. There are 11 waves coming from source 1 and 11 waves from source 2. So the path difference is nothing, and we can see the peaks of both waves are lining up. Constructive interference. As part Q, we can see the waves are arriving there out of phase because one wave has travelled half a wave further than the other. In fact, source 1 has travelled 11.5 waves and source 2 has travelled 12 whole waves. So that's half a wave different. The path difference is half a wave. They're out of phase. We get destructive interference. If we investigate the waves up at point R, up here, now the wave coming from source 2 has travelled a whole wave further. In fact, the wave from source 1 has travelled 12 whole waves to get to point R, whereas the wave from source 2 has travelled 13 waves to get to point R. So the path difference is 1 whole wavelength, but because the peaks are lining up with peaks and the troughs with troughs, we get constructive interference again. And this all gives rise to 2 formulae, which allow us to decipher whether constructive or destructive interference is taking place. For constructive interference, the path difference is always a whole number of wavelengths. So in the formula, m means a whole number of waves. For destructive interference, the path difference is always a whole and a half number of wavelengths. So, constructive interference occurs where the path difference is no wavelengths, 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, and so on. Destructive interference happens where the path difference is half a wavelength, 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, and so on. M can be any whole number. So, here's an example. Waves from coherent sources S1 and S2 produce an interference pattern. Maxima of intensity are detected at the positions shown below. The path difference, S1K minus S2K, is 154 millimeters. Calculate the wavelength of the waves. So what that means is the distance S1 to K is 154 millimeters longer than the distance from S2 to K. Now, this is constructive interference occurring. So we have the formula path difference equals m lambda. That's the formula for constructive interference. Now here, that is the point in the middle, m equals 0. The path difference is nothing. Either side of that, we would have path difference is 1. So that's the first maxima from the center. Path difference is 2 wavelengths. Path difference 3 wavelengths. Path difference 4 wavelengths. But K is positioned where the path difference is 5 whole wavelengths. So M is 5 here. So we know the path difference is 154 millimeters. We know the maximum number is 5. Therefore, the wavelength is 154 divided by 5, which is 30.8 millimeters. And that's how we would tackle that problem. Here's another. Microwave radiation is incident on a metal plate, which has 2 slits, P and Q. A microwave receiver is moved from R to S and detects a series of maxima and minima of intensity at the positions shown. The microwave radiation has a wavelength of 4 centimeters. Calculate the path difference between PT and QT. So here we're trying to work out the path difference. And we can see that at T we have a minima. So therefore, the formula that we're going to use is path difference equals m plus a half lambda. Because one wave is half a wave out of step from the other. So, what have we got here? We're trying to work out the path difference. We know the wavelength, and we need to know the m number. What maxima are we on? So, if we look at this, the maxima in the center is where there's 0 path difference, so m equals 0. Either side of that, we get in the minima, where the path difference is half a wavelength. Then either side of that, the next maxima occurs at where the path difference is 1. Therefore, the minima above that happens where the path difference is 1.5 wavelengths. So path difference equals 1 plus a half times our wavelength, which is 4 centimeters or 0.04 meters. Therefore, the path difference is 0.06 meters. So that's how we deal with problems of constructive and destructive interference from 2 coherent sources. I hope you found this video useful. In the next video, we'll be looking at how diffraction gratings can be used to provide a similar effect. Until then, bye for now.